So in order to help us think about that, we know that f of x equals 1 over x, and as the x value is getting bigger and bigger and bigger and bigger, the y value, the f of x value, is getting smaller and smaller and smaller, and it's approaching 0. And as x is getting smaller and smaller and smaller, more negative, right, so negative 100, negative 1,000, negative 1,000,000, it's getting a really, really small negative number, it's still approaching 0. So in both cases, as x is getting smaller and smaller and smaller here, oops, sorry about that, we know that it's approaching 0. And we need to keep that in mind as we think about finding limits. We have to use this fact to help us. So if I want to find the limit as x approaches infinity of any constant real number a divided by x to any power, I know that as that x number is getting bigger and bigger and bigger and being raised to any exponent, it's becoming bigger, that is going to equal 0. Okay, so the limit, and x has to be now, and remember, has to be a positive real number. It can't be a negative. That would throw it all off. But we know that as I take that limit, it's going to approach 0. All right, so we have to use those two pieces of information to help us find these limits. So we said find the limit as x approaches infinity of 3x minus 1 over x plus 5. Now our key is we want to see things written as some number over x to a power. Okay, so the trick here that we're going to do to rewrite this is we're going to rewrite this as the limit as x approaches infinity. And as long as I do the same thing to everything, I'm not going to change anything. So I'm going to divide every term by the highest power of the variable in the denominator. So in this case, my variable in the denominator is x to the first. So I'm going to divide every single term. There's my numerator. Here's my denominator. And I'm doing the same thing to every term, so it's legal. I'm dividing every term by x. Okay. And remember, I'm allowed to do this. When I take limits, I'm allowed to break them apart and take individual limits. So really, I'm taking the limit as x approaches infinity of 3 minus 1 over x over 1 plus 5 over x. So now, as I use my limit laws, as I take that limit, let me back up there. As I'm taking that limit, I'm plugging in infinity. The limit as x approaches infinity of 3 is just 3. The limit as x approaches infinity of 1 over x, that's what we just learned. We said, oh, that's got to be 0. Divided by the limit as x approaches infinity of 1 is just 1. The limit as x approaches infinity of 5 over x, that's 0. So this limit is just equal to 3. All right, so now we want to find the limit as x approaches infinity of 3x squared minus x plus 4 over x squared minus 4. So we're going to do that same trick. We want to get everything in terms of some number over x to a power. So I'm going to look at my exponents in the denominator. X squared is my highest, so I'm going to divide every term by x squared. So this is the limit as x approaches infinity. I have 3x squared divided by x squared minus x divided by x squared plus 4 divided by x squared all over x squared divided by x squared minus 4 divided by x squared. Now, all I'm doing is making this look different. I am not changing the equation because I'm doing the same thing to each term. I'm essentially multiplying that whole equation by x squared over x squared, which is equal to 1. So that's why nothing's changing. I'm just making it look drastically different, but it puts it in a form that we're then able to work with. So the limit as x approaches infinity of 3 minus 1 over x plus 4 over x squared all over 1 minus 4 over x squared. And again, as I take that limit, I'm taking the limit of each individual piece. So the limit as x approaches infinity of 3 is just 3 minus 0 plus 0. The limit as x approaches infinity of 1 over x. This guy is just equal to 0. The limit as x approaches infinity of 4 over x squared is also 0. The limit as x approaches infinity of 1 is just 1. The limit as x approaches infinity of 4 over x squared is 0. So this limit is also 3. So remember, these limits are talking about what's happening at our end behavior. So these are what we call horizontal asymptotes. We talked about vertical asymptotes in our last section. Now we're talking about horizontal asymptotes. So it's saying if the function value, the y value, is becoming closer and closer to a finite number L for all those sufficiently large and positive x values, then the limit as x approaches positive infinity is going to equal L. And that line L is our horizontal asymptote. So we can define the limit at a negative infinity the same way. If as x is getting smaller and smaller and smaller for sufficiently large and negative x's, then that limit as x approaches negative infinity would equal that horizontal asymptote. And we can have multiple horizontal asymptotes because the left and right end of the graph do not have to be going in the same direction. All right, so here's that one we did before. We found the limit as x approached infinity of 3x squared minus x plus 4 divided by x squared minus 4. We found that that limit equals 3. So here it is, the blue is the graph. Notice we have horizontal asymptotes at x equals negative 2 and x equals positive 2. That's when the function would be undefined. We'd have 0 in the denominators. And what we found is as our x got bigger and bigger and bigger, so going out this way, this graph is going to keep coming down and it's going to get closer and closer and closer to 3, but it's never going to go down below 3 as I get further out. Now if I'm looking at this for this particular graph, I could also say the limit as x approaches negative infinity of f of x is also equaling 3 because as I follow this graph, it's coming down and it's getting closer and closer to that value. So that red line is my horizontal asymptote. All right, so let's try another. We said find the limit and horizontal asymptote of f of x equals 3x cubed minus 2x plus 4 over x squared minus 4. So again, my denominator is x squared minus 4. So if I asked for the vertical asymptotes, it would be when that denominator is equal to 0. So I have vertical asymptotes at x equals 2 and x equals negative 2. Just to review, we like to make sure we remember how to do those things. So now I want to find this limit. So to find the limit, I'm going to first look as x approaches infinity of f of x. And in order to do that, again, I need to divide everything so it's in that format, a number over x to a power. So this is going to equal the limit as x approaches infinity of 3x cubed over x squared, which would turn into 3x. So I'm not writing it all out, but I'm saying it. Negative 2x divided by x squared would be negative 2 divided by x. And then we'd have plus 4 over x squared. My denominator is going to be 1 minus 4 over x squared. So here my limit as x approaches infinity of 3x minus 2 over x, I'm just rewriting it so we can see it a little bit better, plus 4 over x squared, all over 1 over 4 over x squared. So as I plug in my infinity, the limit as x approaches infinity of 3x is infinity. That's a huge number. It's never going to stop. But then I have minus 0 plus 0 over 1 minus 0. So this limit is positive infinity, which means there's no horizontal asymptote because as I go further and further to the right on that graph just keeps increasing and increasing without bound. I can do the same thing and work in reverse and go towards negative infinity. And I can see here the only difference, if I write this as the limit as x approaches negative infinity, I would still have the 3x minus 2 over x plus 4 over x squared, that's a minus, and the 1 minus 4 over x squared. Now I'd have negative infinity minus 0 plus 0 over 1 minus 0, so that would be going to negative infinity, which means the far right-hand side of my graph, if I'm looking at it, right, we know we have an asymptote at 2, we have an asymptote at negative 2. The far right-hand side is somehow going down in this direction, and the far right-hand side has to be increasing in this direction. All right, so let's try another one. So that last one actually had no horizontal asymptote. So not every function will have a horizontal asymptote. This one does. So I have f of x equals 3x squared minus 2x plus 4 over x cubed minus 4. Now we do have vertical asymptotes. We'll skip that one because we want to focus on the horizontals this time. So I have the limit as x approaches infinity. Again, I'm dividing everything by this highest exponent. So this is going to become 3 over x minus 2 over x squared plus 4 over x cubed all over 1 minus 4 over x cubed. So that's, I'm just dividing, and sometimes you do that in your head, that's okay. So as I take this limit, the limit of as x approaches infinity of 3 over x is going to equal 0. The limit as x approaches infinity of 2 over x squared is 0. The limit as x approaches infinity of 4 over x cubed is also 0 over 1 minus, and then that 0. So we really have 0 divided by 1. So this tells me it is equal to 0. So that means I have a horizontal asymptote at y equals 0 as I go off to the right. So the far right-hand side of the graph is approaching 0. As I look to the left, the same thing's going to happen. If I'm doing a negative infinity, this is still going to be approaching 0 because 0 divided by a negative 1 is still going to equal 0. Okay, so to help us see this better, I graphed this for you. So again, we did have a vertical asymptote. We could solve that x cubed minus 4 equals 0. So it's the cubed root of 4 is where that vertical asymptote is. And we see that as we're looking at this, as my graph is going out to the right, as I'm getting closer and closer to positive infinity, it's approaching 0. As it's going to the left, it's getting closer and closer to 0 as well, as x is getting more and more negative. So again, my horizontal asymptote here is y equals 0. All right, so sometimes we have horizontal asymptotes, sometimes we don't. How do we know? So the asymptotes, again, remember, are telling us about end behavior. So when I'm dealing with a rational function, something that looks like a fraction, we have a few criteria. If the degree of the numerator is smaller than the degree of the denominator, so the degree up top is lower than the degree down below, the horizontal asymptote will always be y equals 0. That was the last example we did. We had x squared over x cubed. If the degrees are exactly equal, the horizontal asymptote is the ratio of the leading coefficients. That was the first two examples we did. And then if m is greater than n, the degree of the numerator is bigger than the degree of the denominator, we don't have any horizontal asymptote. And the limit as x approaches plus and minus infinity of f of x is going to plus and minus infinity. There's nothing there. Okay, so this one is saying find any asymptote. So remember, any asymptotes means vertical and horizontal. So our vertical asymptote is when the denominator is equal to 0. So I set x minus 1 equal to 0. I solve, I get x equals 1. So I have a vertical asymptote at x equals 1. Then I need my horizontal asymptote. Okay, well, a horizontal asymptote says I can take the limit as x approaches infinity. This would be negative 3. I'm dividing everything by my x in the denominator, so negative 3x plus 2 over x over 1 minus 1 over x. And then as I evaluate that limit, this goes to negative infinity. So that tells me I don't have a horizontal asymptote. And if I go in the opposite direction, I look at the limit as x approaches negative infinity, I'm still going to be doing 3x plus 2 over x over 1 minus 1 over x. This will equal positive infinity. So there's no horizontal asymptote. Now we also can figure that out using those shortcut tricks, because we know that the degree of the numerator, which is 2, in the numerator is degree 2, the denominator is degree 1. Since 2 is greater than 1, that tells me there is no horizontal asymptote. So that's just a shorter way to help us figure that out. So now here's a graph of that. So on the left, this is the actual function, this blue curve. We knew we had a vertical asymptote right here at 1. And so over here, I have that asymptote not drawn, but there is an asymptote on this. There was no horizontal, right? As we're looking to the right, it's getting smaller and smaller. As we're looking to the left, it's getting bigger and bigger. But notice those kind of make a line. So there is an asymptote here, but it's neither vertical nor horizontal. This is what we call a slant asymptote. Okay, so slant asymptotes, sometimes they're called oblique asymptotes instead, are going to occur when the degree of the numerator is exactly 1 more than the degree of the denominator. Exactly 1. If it's 2 more, 3 more, it doesn't matter. And the way we figure out the equation of this slant asymptote is to use polynomial long division to give us an equation. All right, so we're still using that same equation, f of x equals negative 3x squared plus 2 over x minus 1. We're still finding any asymptotes, so we already knew our vertical asymptote was x equals 1. We knew that the horizontal asymptotes were none, but notice the degree of my numerator is 2. the degree of my denominator is 1, and 2 is exactly 1 larger than 1. So we're going to use polynomial long division here to figure out the equation of our slant asymptote. Remember, when you do polynomial long division, you need to put your placeholders in. I'm dividing by x minus 1, so x goes into negative 3x squared, negative 3x times. Negative 3x times x is negative 3x squared. Negative 3x times negative 1 is positive 3x. I'm subtracting that whole piece, so my 3x squareds are gone. 0x minus a positive 3x is negative 3x. X goes into negative 3x negative 3 times. Negative 3 times x is negative 3x. Negative 3 plus times negative 1 is positive 3. I'm still subtracting, and I do get a remainder here. 2 minus 3 is negative 1. But what I need to focus on to get my asymptote is this part. I don't care about the remainder when I'm looking for my slant asymptote. So my slant asymptote has the equation y equals negative 3x minus 3. Now if you flip back for a minute, you pause the video and go back a little bit and look at our graph again, you'll see that that equation is roughly negative 3x minus 3. The slope is negative 3, the y-intercept is negative 3. So we can have vertical asymptotes, horizontal asymptotes, and slant asymptotes.